Hey guys, we're going to get into the analytical side of finding limits today. What that means is you're going to be looking at problems where you don't have pictures of graphs to guide you through. Okay, so last year when we learned parent functions, this is kind of why. I was anticipating what was to come, and this is part of the reason why we hit parent functions so hard last year. All right, so basically, there's a lot of different procedures for how you're going to go about finding limits when there's no graph given, okay? And I'm going to go through the procedures one by one, starting with the simplest and getting to the hardest at the end, okay? So let's go through this first procedure. So it says, when evaluating a limit as x approaches something, see if f of a is a thing. So what that means is, remember, f of a just means that when x is equal to a, y is equal to some value, okay? And when I say see if f of a is a thing, I mean see if there is a filled in circle at that point on the function, okay? Because if there is, that means it's the limit. So let's start with something really easy. Remember that this number inside, or this expression inside, represents an equation of a function. So in this case, y equals 3 would be the equation of the function. So what does that look like? Well, y equals 3 would be a horizontal line that goes through 3 on the y-axis. Okay? And I'm asking you, what's the limit when x approaches 2 for this function? Well, we talked about this in class today. As x approaches anything, the function would be equal to 3, or the limit would be equal to 3, right? Because it's the y value is always 3. So if I say what's the limit of 3 as x approaches 2, that would be equal to 3 because it's an unchanging function. The next one, what is the limit of x as x approaches -4? This was also on your list of properties from lesson 1.4 part 1, but I'll remind you again. X is the parent function called the identity function, and it goes through the origin, and then it goes 1, 1, 2, 2, 3, 3, etc. in both directions. Like this. Okay? That is helpful information because that means that whatever the x value is, the y value is always the same on the identity function. So if I say what's the limit of x as x approaches -4, I know that the answer is going to be -4. I know that in two ways, okay? I know that because the x and y value are always identical on the identity function. But I also can use limit procedure 1, which says if f of a is a thing, find it and it's the limit, okay? That essentially means take the number that you're trying to find the limit at and plug it into the function, and if you get an answer, then that is the limit. So that's a shortcut for us, big time shortcut for us when we don't have the graphs in front of us. So let's look at this one. So what's the limit of x squared as x approaches 2? So I could go and do what I've been doing here. I could draw the graph. It wouldn't be that hard because it's a parent function, right? This is a quadratic function. Excuse my very sloppy graph here. This is a quadratic function, which means a parabola, like this. And if I ask what's the limit as x approaches 2, it looks like it's going to be 4, right? Well, we don't need to actually have that graph in front of us because what we could do as a shortcut is just plug 2 in for x, and you would get your answer because 2 squared is 4. Okay, so we're going to use that little shortcut trick to help us when evaluating limits because it's going to save a ton of time. So let's try the shortcut here by just plugging in 2 in place of x. And so that would give us 4 times 2 squared plus 3. And when you do that, you get 4 times 4 plus 3, which gives you an answer of what, 19? All right, let me pause for a moment to explain why that works. You know how I made you study all those limit properties the last couple days? Well, if I applied a limit property here and I moved some things around, do you understand that basically I'm doing the same thing as doing plug and chug, like I told you to do here as a shortcut? That's kind of what I'm doing. I'm splitting things up so that this 4 is on the outside. And then I can take the limit of x squared, which I just did on the last slide, and I would get 4 there. And then I would take the limit of 3, which I said is a straight line anyway, so that would be 3. You see how this is working out? So essentially, by just doing plug and chug, I am also applying the properties of limits. I'm just kind of shortening that process. So let's look at example 3. Example 3 is another one where we're going to just try to plug and chug, and if we get an answer, then we know that the limit is equal to that value. So I'm going to plug in 1 everywhere that I see an x. On the top, I would get 1 plus 1 plus 2. So 4 over 2, which is equal to 2. Okay, keep going. Let's just keep using this process. Let's actually do this as long as we possibly can, because it's going to make our lives so much easier. I just want to point out one more thing again. Remember, if there's a square root, you are, using the properties, allowed to move the square root to the outside, like so. So essentially, we're kind of doing that here. We're going to do plug and chug, and we're going to get 0 plus 4 on the inside, and square root of 4 is equal to 2. So our limit would be 2 for example 4, part A. We're going to try the same thing down here and do plug and chug. So we have cube root of 2 times 3 squared minus 10. Be careful with your mental math. 3 squared is 9 times 2 is 18 minus 10, so 8 here. And the cube root of 8 is positive 2. So everything seems to be working out pretty well so far. Let's see how it works with trig stuff. In your notes, I'm going to ask you before we start the trig questions to pause and see if you can fill out this table correctly. So you can pause the video here, try to fill out this trig chart, and then hit play when you're ready. Okay, I'm going to fill out the trig chart for you real quick. I'm not going to really explain a whole lot because hopefully this is stuff you already know. But remember that with trig stuff, it's very, very important that we memorize these values, because on the AP test, you're not going to be allowed to use a calculator for a significant part of it. So you have to make sure that you know these by heart. That way, when the test comes, this isn't a barrier for you. Okay, so check your answers with mine. See how you did. If you still don't quite have it memorized, that's okay. Just keep working at it. Okay, we did that because this is the next thing. We're doing plug and chug to find our limits for trig functions. So I'm going to be plugging in 0 to the tangent function, which means I would need to know what tangent of 0 is. Tangent of 0 is 0. Okay, plug in pi. So I would have pi times cos of pi. And I need to find cos of pi first. So cos of pi is equal to cos of 180 degrees, and that would be -1. And times by pi, and you get -pi. Okay, last example with trig stuff, I have 0 that I'm plugging in. So sine of 0, quantity squared. Sine of 0 is 0, so my answer would be 0. Unfortunately, I have to ruin all the fun because you can't just do plug and chug every time. That's because not all functions are nice functions, right? As we saw in the examples that we did today in class, a lot of functions have holes in the graph, have discontinuities, etc. And those are not going to be apparent if you're doing plug and chug. So you're going to run into some issues. So to begin this, I want you to do a quick review of what you can do with this expression algebraically, okay? Because this would be an example of a function that would have like a weird thing going on, a hole in the graph or an asymptote or something like that. So algebraically, what could you do with this? Don't you dare say you can cancel an x. I will freak out. You can't just cancel an x, remember, it has to be a product. Anyway, what you can do is you can factor the top. And once you factor the top, you will notice that you have x minus 2 and an x minus 2 that cancel. And so you could simplify this whole thing down to just x plus 2, right? Okay. Algebraically, this first fraction is equal to x plus 2. Graphically, they are not quite the same, okay? Graphically, you have x squared minus 4 over x minus 2. You have y equals x plus 2. They're going to look a little bit different on the graph, okay? And the difference is going to be that they're both going to be linear, but this first one is going to have a hole in the graph because x can never equal positive 2 because that would make a 0 in the denominator, all right? Which is fine, okay? If one graph is the same as the other, but one has a hole in it and one does not, it's not going to affect our ability to take a limit. Because remember, limits aren't changed when there's a hole in the graph, right? So basically we're dealing with this theorem. The theorem is if you have a function that's complicated, okay, if you have a function that's complicated, but you're able to simplify it down algebraically, the limit of the complicated function and the limit of the simple function are going to be the same. Because the only difference between the two is that there's probably a hole in the graph or something at that point. And that does not change our limit value. So because of this, we're going to use the trick where if you can't do plug and chug, you are going to try to factor and cancel so that you get an equivalent expression, but a simpler version of one. So let me just get to an example where you can see it in action. So for example 6, I'm going to try plug and chug. And I'm always going to start with trying plug and chug, by the way, because if I can do it this way, it's going to save me so much time. So if I try to plug and chug on the top and on the bottom, I'm going to get something I can't compute, right? Like, what does that even mean? 0 over 0 means nothing. So we're going to go back and say that that didn't work. Let's go to option 2. Option 2, you're going to factor the top and the bottom. Now notice I am still writing the limit symbol because I haven't actually taken the limit yet, which means that I need that there in my work. So the top gets factored like this. I wrote the sum of difference in cubes formula up here because it's not something you'll have to memorize. But this is how the top would factor. And I notice that once I factor the top out, it will cancel with the denominator. So algebraically, I can take the limit of the simplified thing, and it'll be the same as the limit of the complicated thing. And I have a graph on the next slide to show you why. So this thing is a lot simpler to deal with. Now I'm going to try to plug and chug into the simpler thing. And this time I am able to get an answer because it's something that I can actually compute, and my answer would be 3. Still a little confusing to understand that this is actually going to work, but here's a picture of why. So the first function is the one that wasn't factored. You'll see it's a quadratic, it's a parabola with a hole in the graph. And the second one is the simplified version, and it's just a really nice, pretty parabola. They are the exact same graphs. One has a hole, one doesn't, but that hole in the graph does not affect our ability to find the limit, right? The limit as x approaches 1 on this first graph is exactly the same as the limit as x approaches 1 on the second graph. So that's why this process works. So let's just keep going and using this process. Remember, you're going to try to do plug and chug first every time because it's way faster. This time it didn't work. This doesn't make any sense. So we then have to go to limit procedure 2, which is try to factor and cancel. Okay, factoring the top, I would need, is this right? X plus 3 over, or times x minus 2? I think so. Yeah. So we're going to cancel the x plus 3's, and we're going to take the limit of the simplified function, which is x minus 2. And I can plug and chug into that, and I would get -5. Okay? All right, what might happen here is you might try to plug and chug, like on this one, and you get 0 over 0. And then you might try to factor, like we've been doing. So the top would factor like this, the bottom stays the same. But what might happen is you might get something that doesn't cancel. And then you're kind of back where you started, where you can't plug and chug because you still would have a 0 on the bottom. So please understand, if plug and chug doesn't work and you are not able to factor and cancel, then you have a situation where the limit does not exist. Okay, so this one would be a D and E because I can't do anything with it. Therefore, the limit doesn't exist. Okay. This next part is where our algebra skills are going to really be put to the test. So if we try direct substitution, aka plug and chug, and that doesn't work. If we try factor and cancel, and that doesn't work, then your third option, limit procedure 3, is you're going to use conjugate multiplication. Okay? This happens most of the time when you see radicals going on. So you will notice if I plug and chug, I would get something like this. And already I can't compute it because I have a 0 in the denominator. Obviously I can't factor anything from this because there's nothing to factor. So we're going to use conjugate multiplication. Remember, a conjugate is multiplying by something, typically with a radical, but changing the sign in the middle. So in this case, I'm going to take the radical, and I'm going to multiply by radical x plus 1 plus 1. So I'm going to change this sign in the middle, and I'm going to multiply by that thing on the top and the bottom, okay? As I'm working, I'm going to explain why I'm doing this. I'm doing this because I want to algebraically modify my expression because the way it looks right now, I can't do anything with it. So I'm trying to come up with something that I can actually work with. So I'm going to start with multiplying the radical times the radical would just equal the inside part. And then I would have radical x plus 1 times 1, so that would be plus radical x plus 1. Negative 1 times the radical would be negative the radical. And negative 1 times 1 is negative 1. Okay, I got simplifying to do up there. The bottom, I'm not even going to bother multiplying all that out because I can tell that nothing's going to combine as far as like terms go, so I might as well just leave it there. Okay. On the top, I'm going to simplify these two radicals here in the middle, cancel each other out. I have x plus 1 and a minus 1, so these ones cancel each other out. and that leaves me with just an x on the top. Then I actually can cancel an x from the top and an x from the bottom to even simplify further. So my simplified, completely simplified, or you could call it algebraically modified equation looks like this. Okay, it's totally different than what we started with. It's algebraically equivalent, so it's fair game. So I'm going to try plug and chug again. So if I plug in 0, I'm going to get something that looks like this. The square root of 1 is 1, and 1 plus 1 is 2. So I'm actually getting an answer, which means that I have now found my limit.